Welcome to our new and Wolfram Language 12 webinar series. Today is the third session in a four-part series that covers significant areas of new and expanded functionality in Mathematica and the Wolfram language. My name is Jamie Peterson, and I'm the Technical Programs Manager for Wolfram U, a free and open learning hub that features interactive courses, video classes, and webinars like this one. Thank you for joining us today. Today's topics cover the expanding calculus and algebraic computation functionality in the Wolfram language. But today we'll be showing you the latest in scientific visualization for complex valued data and functions, geographic data, and molecular structures. Joining us are Devendra Kapadia, manager of our calculus and algebra group, Adam Strabonsky, symbolic algorithms developer, Brett Champion, visualization manager, and Jason Biggs, lead developer for chemistry content. Okay, I think we're ready to get started with our presentations. Devendra and our calculus functionality is our first topic up. Devendra, I'm ready to pass things over to you.
Thank you, Jamie. Hello, everyone, and welcome to this webinar. This is Devendra, and it's my great pleasure to speak to you about the calculus features in version 12. Now, calculus is probably the most popular part of Mathematica and Wolfram Alpha for students. And in fact, many people start using Mathematica by using calculus, by integrating a function or something of that sort. And then they go on to use it forever, basically. So this is a very, very popular area of Mathematica. But for version 12, we set a slightly more ambitious set of goals. So first of all, we said we would like to make our functions more powerful and by adding more algorithms and functions and other things. We also wanted to come close to applications like image processing and other things. The third point is that very often people find our documentation, but then they cannot answer their own questions very easily. So our question was, can we make the documentation absolutely world-class as it already was, but make it even better? And finally, we said, okay, someone like myself is a teacher and have taught calculus for many years. Can I actually give someone to a full course in calculus and bring them up to speed with how to use Wolfram language for calculus? So that's the set of goals we had for ourselves. And so to keep those in mind, when we talk about this seminar, so first of all, we said, let's implement new algorithm functional limits, that integrals, that will make them more powerful. We looked at integral transforms, which appear in image processing, for example, the Hunkel transform and the Radon transform. We've added more than 5,000 documentation examples. That's made the whole system much more usable. And then finally, we have gone a step further and actually delivered a full-scale Wolfram U calculus course, which has proved to be very, very popular. So my goal today is to try and give you a very brief overview of all these very nice features of version 12 in the hope that you'll find this version absolutely first class to use for calculus. Okay, so let's begin with limits. So here's a limit which has basically been very difficult to do in any earlier version. So the limit is for a function e to the polygon of x over x. Now, if you plot the function, it looks like it's going towards some kind of a limit over here, around 0.6. But the question is, how do you actually compute this limit? Now, when you compute limits, you probably want to use the L'Hopital's rule, but in Mathematica, we prefer to use series expansions. But then for something like this, in 1996, the Swiss mathematician Dominic Grunz, working at the Swiss Federal Institute of Technology, actually gave a much nicer idea. And what Grunz said is that if you look at this expression over here, and you kind of switch off this polygamma over here inside, and you try and expand the other e raised to polygamma, you basically get something like e raised to x times x to the negative 1/2. Then you do another expansion, plug back the polygamma, the x cancels out, and lo and behold, you get back this very nice limit for the function. So the Grunz algorithm is a very important feature of version 12, and we have a world-class implementation of this, not just for elementary functions, but also for special functions. Okay, so on to the fact that limits seldom exist. The fact is that many limits will not exist. So for example, here's a function which is pretty much beyond any kind of limit computation. It's an oscillatory function. And if you look at it around the origin, you see that to the left of the origin, you actually have the function approaching 0. But to the right, there is wild oscillation. And the question is, how do you show that this limit does not exist? Well, in earlier versions, that is a bit hard, but now there are several ways to do it. So for example, you could show that the limit from the left is 0, the limit from right is indeterminate, so that says the limit does not exist. Or you could show that the lower limit, that's a new feature, is -1, and the upper limit is 1, that's the oscillation over here. But whatever it is, all this put together tells you that the limit at 0 does not exist. So that's the full language of limits that's possible with the new version. Okay, now we went a step further and said, how about multivariate limits? Now that's a standard topic in advanced calculus. We have not actually had this happen before. We've got all the functionality underneath, but we decided to go ahead now and actually implement a multivariate limit function in Mathematica, and that's a pretty difficult limit, but we quickly get the answer to be -1/2. You can see over here, the function does oscillate around 0, but eventually it settles down to limit -1/2. So this is a pretty important feature which will make it useful for advanced calculus students to use the limit function in their classrooms. Okay, now one last point over here is that we actually have sequence limits. So let's say you have the sequence over here, and this sequence over here is clearly oscillating wildly, but as far as the upper and lower limits are concerned, there's no difficulty at all. You can work them out quite nicely, and you can see over here that this upper limit, which is in terms of root object, gets caught very easily by the new discrete limit function. Okay, so I talked about L'Hopital's rule a little early on, but there's actually a discrete version of the L'Hopital's rule, and that's something called the Stolz-Cesaro rule. So this rule says that if you have a limit and both numerator and denominator approach infinity, then you can take a difference, not a derivative, and get back the answer. And we use this very simple idea over here to actually get back a very nice answer for this rather complicated limit. Basically, the Stolz-Cesaro helps us to peel off the outer sum, and then you get back the answer 4 in just a flash. Okay, so that's the Stolz-Cesaro rule. And the other point, of course, is that we have support for nth derivatives in this new release. So in earlier release, you could find the first or second derivative, but here's a second function over here, and the nth derivative is this rather messy expression over here. But as soon as you put n to be a specific integer, you get back a very, very nice expression. And around a few years ago, Michael Berry, the famous physicist, pointed out that, in fact, these high derivatives generate oscillations. So that's the oscillatory behavior of these higher derivatives. So you can compute the nth derivative, you can specialize, and you can study the oscillations of these higher derivatives. Okay, so with derivatives, the question was, what can we do with them? We got nth derivatives, what do we do with them? But then it turns out around 1930, the famous logician Emil Post, in fact, derived a very nice formula for inverting Laplace transforms. That's a very, very difficult problem. And he said, you can use the nth derivative like I've done over here, the kth derivative in this case, and a limit computation, discrete limit computation to actually get back the Laplace transform, the inverse Laplace transforms for many functions. So here's a simple example. You have 1 over s minus 1, and it quickly gives back this very nice answer for the Laplace transform inverse of 1 over s minus 1. Now, you might say, oh, that's a very difficult computation, but it turns out that you can actually take very high order derivatives and get a pretty good numerical approximation for the nth derivative without too much work. So the Post method is actually a practical method because you can actually use higher derivatives to work out the approximate inverse Laplace transform. So we have a very nice set of new limit functionality. We have nice derivatives. And the next point, of course, is how about integrals? Well, integrate has, of course, been the most powerful function in calculus, the most popular function in calculus. So question is, what more could we do with it? Well, we added these very exotic kind of integrals in version 12. That's an algebraic integral, give back a nice answer like over here. And that's a Fresnel integral, also gives back a nice answer. In fact, we tested against around 70,000 integrals, found 1,000 that didn't work, and then tried to make them better and better. But this is a significant achievement for integrate because this is already so powerful. What more can you do with it? Well, we actually have taken it to the next step over here. Okay, so a few months ago, before version 12 release, Michael Trott walked into my office and said, you know, Devendra, we've been here for 30 years. And you know what? You still don't know how to generate an arbitrary constant integration. So I said, okay, Michael, we do it for you. So now in version 12, you can say generated parameters goes to C, and it gives you back this integration constant in the result, which everyone loves so much. And the point, of course, is that this answer over here represents a family of curves. So as the C varies, so does the integral curve in the plane. So the point is we have a nice feature, a long-standing demand, which has been fulfilled in this new release. But of course, things are not so simple. So if you do a triple integral like over here, then you might get back these functions of y and x in the answer. So really speaking, this process over here generates constants by solving simple PDEs. We have cracked a major problem, not just for single integrals, but also for multiple integrals. Now, one point, of course, is that people who use our calculus functionality are often applied people. So we said, what can we do for them? So we looked at these so-called Hankel transforms. You see, in version 11, we introduced the Melon Transform. The Melon Transform is pretty useful, but a bit mathematical. So Victor Adamczyk, who was working on this Melon Transform functionality, told me, you know, Devendra, we can actually implement these Hankel transforms quite easily. But the point is, what are Hankel transforms? Well, Hankel transforms are basically radially symmetric Fourier transform integrals. So here's a radially symmetrical function. It's radially symmetrical over here. You find a Fourier transform in version 12. That's a nice plot of the Fourier transform. And in fact, it is a Hankel transform computation underneath. So Hankel transforms let us do very nice Fourier transform computations to understand this very deep kind of mathematics associated with Fourier transforms. Okay, so around a century ago, in 1917, actually, the famous Austrian mathematician Johann Radon published a paper in which he said, his problem was to try and compute the value of a function given the integrals of that function along straight lines in the plane. Now that looked like a piece of very abstract mathematics, but as time has rolled by, in fact, this has become a key feature of medical technology. So when a patient goes for a CT scan, let's say that's a section of the patient's body, then the doctor will put bundles of x-rays across that section in different directions. And the question for the CT scan machine is, from that mess of information, how do you get back the patient's actual image? And of course, the doctor can then come in and decide that it's some serious disease like cancer or maybe pulmonary fibrosis or whatever. So that mathematics over here is in fact now available in calculus. We have the Radon transform, which computes the Radon transform in a particular direction in the plane. So the P over here and the phi actually specify different straight lines in the plane. And from that, you can get back the inverse Radon transform, and that's the original function over here. So this is quite an achievement. See, what happened was that Melon transforms gave us Hankel transforms. And then Hankel transforms give us Fourier transforms. And then those Fourier transforms are used to compute inverse Radon transforms. So this has been really a very nice release for me because we've seen things working step by step in a certain order, but now we have Radon transforms, which are actually very, very important in modern medicine. Okay, so all that's very good, but the question was, can we make our functionality much easier to use or not. And so for version 12, we actually had around 5 interns who worked full time with us to solve 6,000 problems from a standard popular textbook. And having done that, we then picked the best few hundred and put them into the pages for limit, d, and integrate. So these pages now are actually a very nice way to learn calculus. They're a complete introduction to those functions, and I hope they'll really help everyone. So we have put a lot of effort into documentation. We have tried to actually do a good job on all this. Now, the next point was we have calculus, but calculus is not just limit, d, and integrate. We actually have 250 mathematical functions. Well, we had another intern, a set of interns who worked on those 250 functions and produced around 4,000 new examples for these new pages. So now you have a kind of encyclopedia of special functions built into your copy of version 12. If you upgrade, you simply get the best possible collection of special function examples in the world, basically. So that's a kind of collage of all those, a word cloud of all those 250 functions. So we've tried our very best to make the documentation as useful as possible. Okay, one last point over here is that I've taught for a long time. So around a year ago, my manager, Roger Gurmanson, said, Devendra, why don't you develop a new calculus course? So I said, okay, let me try. And this course is all thanks to from you people over here, Jamie and Cassidy and other people who have really worked hard to make this course possible. So we have a full-scale introduction to calculus available on the web. And in fact, you can get a very nice certificate by completing the course. Lots of people are doing it. On my estimate, we get around 8,000 people coming to the website every month. This is a very nice way for you to learn calculus. It's totally free. There's been no problem at all in getting a certificate. And I think that this is where we go from here on. We'll try and develop more and more courses to make our calculus functions even more visible to the world. Okay, so that brings me to the end of this presentation. So I hope you'll agree that the version 12 functions are much more learnable and applicable than what we had early on. And I'll just take a minute now to show you the features page where you can actually look at these examples in much more detail. It's a very nicely done page. Lots of effort went into it from my team. And I'm very proud to look at all the examples again, the limit examples, the discrete limit examples, the D examples, integrals, integral transforms, Wolfram calculus. I hope you'll find some time to go through all this and actually, enjoy the calculus features in version 12. So really, that's all I have to say for this presentation. It's been a great pleasure to speak to you, and I, of course, will address when I see lots of nice comments coming up. I'm going to try to address them as soon as possible. But do try and look at the page over here and get some feel for what's changed in version 12. So thank you very much. I'll stop over here.
Okay, so let me start my part of the talk. I will talk about computation, algebraic computation in version 12. My name is Adam Strzewoński. I'm symbolic algorithms developer, and here's the plan for my talk. First, I will talk about equation and inequality solving and exact optimization. In those two categories, we have mainly extensions of scope and improvements in the existing functions. Then I'll talk about equation manipulation and equational logic proofs. These are entirely new functionality in version 12. So let me start with equation and inequality solving. First, we can now find topological properties of solution sets of systems of polynomial equations and inequality. So for instance, here's an inequality, and cylindrical decomposition is a function that computes for us explicit solution set of this inequality. We have, so it always starts with, say, bounds on the first variable, then bounds on the second variable, and this is an explicit description of the solution set, and we can visualize the result. This is the algebraic, semi-algebraic set that this inequality describes. So now we can compute the boundary of this solution set. So we tell cylindrical decomposition to compute boundary, and here we get a equation and inequality description of the boundary of the solution set. And here's the boundary, here's what it looks like. And we can see that the solution set has three components from the plot, and indeed we can compute cylindrical decomposition of each of the components. So here is the first component, here is the second component, and here is the third component, and here is a plot. Now, thanks to the functionality of cylindrical decomposition, we can actually color the components differently because we have explicit solution for each of them. Okay, here now another addition to equation inequality solving function is the ability to specify vector and matrix inequalities. So for instance, here's a problem specified in a vector language. We are looking for two orthogonal vectors such that component-wise vector y is between minus vector x and plus vector x. So for instance, here in the visualization, this is the red vector is plus x, blue vector is minus x, and the green vector has to be in the box defined by these two, by red and blue vector. And norm of vector x is 1, and here we specify that we are looking for vectors. And we get the solution for the vectors, and here the solution is visualized. We can also fully solve system of vector inequalities using reduce. We get the solution written in terms of coordinates of the vectors. And here's the visualization of the solution set. Okay, here are other improvements in equation inequality solving. So we have added new algorithm for solving large triangular polynomial systems. So here is a timing comparison. It's on a logarithmic scale. So you can see version 12 is 5.9 times faster for problems with 2 variables. We chose triangular problems of degree 7 with randomly generated coefficients. For 4 variables, it's 54 times already faster, and for higher number of variables, version 11 was timing out at 1 hour. Version 12 can compute here for 5 variables in less than 100 seconds, for 6 variables in less than 1000 seconds. Another class that we have extended the functionality for is Diophantine equation with irrational coefficients. So now we can specify the Diophantine equation, and some of the coefficients are irrational, and we can solve for positive integers. This is another thing that was added in version 12. We can now specify domain like positive integers, positive reals, negative reals, and so on. So, and here's the solution set. So, positive integer solutions, and here is slightly more complicated equation in 4 variables. We also are looking for integer solutions, and it has only 2 solutions. Another area where we have extended the functionality is solving inequalities involving transcendental functions, especially functions that are meromorphic. So now we can exactly find the roots and hence solve inequalities involving meromorphic functions. Here's the solution, and here is a system involving a symbolic derivative. So this derivative does not have a closed form solution. Nevertheless, we are able to find its zeros exactly as those root objects. So let me demo the representation of root objects in version 12. Now we get such a blob with numerical approximation instead of the large root object that it represents. So if we put our cursor on the blob, we can see the exact representation of the root object. And here we visualize the solution. So here are the roots of the derivative, i.e. minima and maxima of the function. Now, optimization of periodic functions. That's another class of functions for which the computation has been improved. So here we have a combination of trigonometric functions. You can see that the whole function is not periodic since they are composed with some non-periodic function. Nevertheless, we can we can find the minimum. And here it is. It again uses the root objects, which would be quite large here in the old root object representation. And here we visualize the solution. That's what the function looks like. And here's the minimum. Another class, so we can find maximum value of combination of periodic function with incommensurable periods. So we have sine of square root of 2 times x and cosine of 3 times x. So the ratio of the periods is not a rational number. And so we get the maximum value, which is never attained, but this is the global maximum value of this function. And let me compute the value, which takes a while. On this computer. Okay, so let me then talk about the next example while this is computing. So we are looking for minimum value of combination of periodic functions with commensurable periods now over the integers. So we can see that these are the values of the function over the integers, and this is the minimum value. Let me just, okay, here this finished computing. I will not start the second example, just show the answer. Here it is. Okay, next class of problems for which the functionality was extended in version 12 is optimization for over vectors and matrices. So here again is a minimization problem specified in the vector language. Here again, vector inequalities, dot products, norms. And here you get the vector solution. And this is the visualization of the solution. This is the optimal solution which is orthogonal to the x with norm 1 and between minus x and x. Here is how we solve optimization problems for matrices. So this encodes the sort of finding maximal eigenvalue of a matrix right from the definition of eigenvalue. And here we got the maximal eigenvalue and the eigenvector. And we can compare it with the computation done by the eigensystem function, and indeed the maximal eigenvalue is here. And here we maximize the determinant of a positive semi-definite 3x3 matrix. So this matrix inequality here means that we are looking for positive semi-definite 3x3 matrix, and the trace of the matrix is supposed to 1, and we are maximizing the determinant. And here's the result. Okay, other improvements in exact optimization. We can optimize univariate elementary function over the integers. For instance, this function, here is the optimum, or function involving arctan and log. Now here is optimization problem involving transcendental functions with 2 variables. We maximize this function over the whole R2, and here is the maximum. We can visualize it. Here is what it looks like. And now we can solve another class of problems, is problems involving function composition. So we can have quite deeply composed function, and we can compute maximum of this function. Here is the plot and the maximum point. Okay, now for completely new functionality, we have added functionality for manipulating equations and inequalities by hand. So this is something for the K-12 school students. For instance, you can now solve a system of linear equations by hand, as one is taught at school. Multiply the second equation by 2, subtract the result from the first equation, now divide sides by 5, and we get the solution for y. And to get the solution for x, we multiply the last equation by -3, add the first equation, and divide both sides of the equation by 2, and we get the solution for x. And we can do the same with inequalities. So for instance, here we have an inequality. We can subtract b from both sides. We can divide both sides of inequalities by a. Now we get piecewise expression as a result, because the result depends on the sign of the constant we are dividing by. And we can add equation to an inequality, and we can add two inequalities. You can see that add sides will automatically reorder the second inequality to be able to add it to the first one. And one more function from this class is apply sides. This one is a purely structural function, so it just applies the same function to both sides of equations, and that doesn't really mean that the equation we derive this way is true. That's just structural operation. For instance, we can here apply sides to equation inside conditional expression, or we can apply a function to each inequality in piecewise function. And okay, so now let me talk about equational proofs. We have introduced functionality for representing equational proofs in axiomatic theories. So for instance, let's take an axiomatic theory of Boolean algebra from our collection of axiomatic theories. Here are the axioms. Now we can prove this statement from the axioms. And we get back a proof object. So it's a proof with 83 steps, and we can now look at some information derived from the proof objects. For instance, here is a graph of the proof that shows how each statement in the proof was shown based on other statements on the proof, or here is data set which displays all the details of the proof steps. And here in the second example, let me show proof that so here we have axioms of the group theory. So we have axiom for the right-hand side unit, and now we can show that left unit is also that the right unit is also a left unit. So here is the proof. Takes 11 steps, and here is a proof notebook. So this is something that will show the proof in human readable form. So this is something that we can read, so we can solve the exercise where we are asked to show that a right unit is also a left unit. Here's a proof in 11 steps. And further information is available here at our web page. It's algebraic computation, and we can see all the examples I have shown and some more. So thank you.
Thank you, Adam. I think we've had a lot of really good questions coming in, and I think maybe Devendra wanted to take an opportunity to respond to some of those.
Thank you, Jamie. Yes, so Adam gave a wonderful presentation. Adam is absolutely fantastic. You know, Adam doesn't make mistakes. We have a joke in our group that Adam is absolutely perfect, and you're very lucky to have had a chance to, listen to him today. But my point over here is that you actually can do a lot with version 12. Thank you, Dara, for your comment about the version 12 presentation. You really liked them. Thank you for that. Thank you, Bruce, for your very positive comments about the seminar. I noticed that Ellie asked about where can I find information about generate parameters, what has changed? Well, I recall that I had forgotten to add an example, and I recall adding it. There should be an example on the generate parameters.html page for you for integrate. If not, do email us, we'll send you more information. But this presentation says it all. Just do generate parameters goes to C, and you should find your answer to your question. Then there was another question about the inverse Laplace transform, which is a fantastic suggestion. That's something I'm working on right now. So while you're thinking of 12.0, I'm thinking of 1 year from now, and I'm thinking that the inverse Laplace transform is a very, very important feature for the future. So Naresh Patel, thank you very much for that suggestion. Inverse Laplace transform is very much on our minds. We will work on it very soon. So I think that the Radon transform seems to be very interesting for some people. I agree that it would be good to have it in higher dimensions. The limit syntax is what you do by hand probably, but if you don't prefer that, you could just use ordinary notation, just type in discrete limit or limit, and that should work just fine. So thank you for all the questions. It's been great to have all of you over here, but I'll give Adam a few minutes to talk about his questions, what he received from people, and then we'll close up over here. But thank you, Adam, for an excellent presentation.
Thank you, Devendra. Thank you very much. So one question that I saw here is a question about the root object. So let me talk about this more, if I can get. Okay, so here's an example. So what does this little square root in circle mean? So that's a representation of an exact number of a root object. So this is just numerical approximation of the first 3 digits. But here, if we look at it, it's the root object that has been known in Mathematica since version 3. In version 11, it would be printed as root, the one that we are showing here in the tooltip. The new representation in version 12 is this blob. So this is something we can copy it out from here. We can take numerical value of it, for instance, with 100 digits. And the input form of is the root objects that we could see in versions 11 and earlier. And this representation in version 12 is for root objects and for algebraic number objects.
First up here is Brett Champion, our visualization manager. And Brett, I think we're ready to hand things over to you.
Thank you, Jamie. So we're going to start by looking at complex visualization, which is entirely new in version 12. And then following that, we'll look at geographic visualization, which we've been sort of incrementing upon for the past couple of years. But we'll start with complex. And so, looking at sort of Adam and Devendra's talks, there's a lot of symbolic things that have gone on. And as a company, we take a lot of pride in dealing with equations and formulas in sort of their most general form, not just over the reals, not just the real valued parts of things, but thinking of things as their general complex behaviors. And so occasionally we'll get reports from people about didn't simplify something down to the way that I thought. And frequently the reason for that is that the simplification that they had in mind really only applies under certain conditions. It's perhaps true for real numbers, but not for complexes, or it's only valid in part of the complex plane. And so on the symbolic side, we've had like really strong support for complex valued operations. And the visualization side sort of hadn't followed that into the same depth. And we decided that we wanted to remedy that. And so for version 12, we started working in on complex specific visualizations and making it easier to work with complex numbers and complex valued formulas and functions. And so in version 12, we implemented and introduced 5 new visualization functions: complex list plot, rem plot, abs-arg plot, and then complex plot and complex plot 3D. And all of these have sort of obvious analogs in the 2D, in the real valued realm, but hopefully allow us to do things a little bit easier when things become complex valued. And so the first and sort of simplest of these functions is complex list plot. This is essentially list plot, but for complex valued things. And so this is good for visualizing discrete complex numbers that may arise in various forms. Typically, they're going to be roots of some sort, whether it's sort of an explicit set of results coming out of insolve or something else. And so coming up through school, we always learned that a polynomial of degree n has n roots. If you introduce transcendental functions, then things get a lot more interesting, and because of periodicity, you get frequently an infinite number of roots. And so here we're looking at the values of z for which sine of cosine of z is z. So basically where sine is cosine inverse. And we're just looking inside a disk of radius 10. And it turns out that there's 727 such points. And then we can just sort of easily throw that into a plot. I'm not going to show all 700 of them, but just to make clear what the input to complex list plot is, we'll take the first 10. And so this is just a list of complex numbers. And then complex list plot does the obvious thing. Prior to version 12, you could do the same thing by using list plot and applying rem and manually extracting the real and imaginary parts and then plotting those as XY pairs. And this just streamlines it, makes it a little bit simpler. So the other thing that this does is that this, because complex numbers have sort of this dual way that we think of them. So we think of them in terms of a Cartesian sense with real and imaginary parts, but then we also think of them frequently as a polar representation with radius and angle. And so because of that, then we added the ability for complex list plot to use polar axes instead of just the Cartesian axes that list plot would normally have. And so even though this is in some ways a very simple function, we're looking for ways to sort of take advantage of the fact that we know that we have complex numbers coming in and thinking of things in that sense. And so then the next couple of examples are, like I said, these are roots again. They don't necessarily think of them necessarily as roots, but they are. And so if we take, say, a 500 by 500 matrix whose entries are randomly chosen from -1 to 1, then we get 500 eigenvalues. Those are roots of a polynomial with real coefficients. And it turns out that those are sort of evenly distributed in this disk. Because it's real coefficients, then on the polynomial underlying the eigenvalue computation, all of the solutions are going to come in conjugate pairs. And so you sort of see we have a symmetry across the x-axis here. I suppose I should say across the real axis. If we do it with complex valued, then we don't necessarily have the conjugate pairs, and you get sort of this nice evenly distributed set of points inside of a disk, which is, I think, a really cool sort of feature that comes out of this. So the next function I want to look at is reimplot. I have seen variants of this come up numerous times, where somebody plots the third root, or x to the 1/3 of x from -3 to 3, and they only get half of a plot. And that's because x to the 1/3 is not cube root in the sense that you learned about as a kid. And so I'll just mention that we have that as a built-in function for probably a couple of years now, that this is cube root where sort of the, which has sort of the symmetry going from positive to negative. But this one is using principal values and whatnot. And you don't have anything on the left-hand side for the negative values of x. And so reimplot is sort of a hybrid visualization, reimplot and absarg plot, in that they are expecting the function to be complex valued, but we're plotting over a real valued domain. And so it's quite frequently that you're thinking of, so some parameter space that is real valued, but the functions that you're using may be complex valued for part of that domain. And so if we do reimplot of this function, then you see we get two curves out of this. We get this solid line, which is the real part, and we get a dashed line, which continues along the x-axis, the positive x-axis here, which is the imaginary part. And this has sort of reimplot specific options for controlling what the real and imaginary styles are, how to do some of the labeling. But so I can make it so that, say, the real part is red, and the imaginary part is solid blue, not dashed at all. And so then you can see that there's nothing, when you did plot, there's nothing over here because there's this imaginary component that isn't representable. Absarg plot is very similar to reim. The basic concept is the same, but instead of showing that the result using the real and imaginary parts, we're looking at the polar representation with the absolute value and the argument. And what this one shows that sort of the reim plot didn't, or at least shows sort of very well, is that for x to the 1/3, the absolute value of the function is the same for positive and negative values of x. That the absolute value is symmetric across x equals 0. And the other thing that this sort of shows, and this happens a lot, in this function, and coming up with examples where it doesn't happen is, takes a little bit of work, is that you'll see that each of these sections is sort of its own color, and it's a constant color. And so what that means is the color here is encoding the argument. So red is corresponding to 0, and this yellowish is corresponding to pi/3. And so for positive values, then because the argument is 0, you know that this is a real valued function on this half, that this is all real values. On this side, the 1/3 means that it's a constant angle that's going off at, that those complex numbers are sort of shooting out in a ray from the origin in a fixed direction of pi over 3. And so if we look at the other two roots of the other two branches of the cube root, then I mean, you see that the absolute values behave exactly the same as for the principal root. And really all that's changing is what direction the solutions are going in. So here it was 0 and 1/3. Over here it's 2/3 and pi. And then over here we, pi and minus pi. And then over here we have minus 1/3 and minus 2/3. And so, like, sort of looking at these, you can get sort of different insights and different views into how a complex valued function may behave over a real valued domain. But the real, fun function is complex plot. This is the one where we spend a lot of time looking at pretty pictures. Looking at pretty pictures is the worst part of the visualization job. We hate looking at pretty pictures, just hours upon hours. But anyway, so this is complex plot and complex plot 3D are looking at complex valued functions over complex valued domains. And in both of them, the color, similar to Ab's arg plot, is representing the argument. And so let's turn the legends on here. And so as before, we go from minus pi is turquoise through 0 red to turquoise again at pi. And in this case, we also have sort of a secondary gradient going on, which is sort of full saturation of the colors at 0, when the absolute value is 0, and then it lightens up and fades out as it increases to infinity. And so you can, you get a pretty picture. And we'll talk in just a bit about how to interpret this pretty picture, because it's sort of hard perhaps to read off actual values from these colors. But first, I want to, as I was saying earlier, we get people who comment that I expected such and such to simplify and it didn't. And one such simplification is that log of z to a power is the power times log of z. And it turns out that this identity that we all learned when we were 13 years old or thereabouts is only true when z when the real part of z is positive. And if we do a complex plot of both of these expressions over the same range, then you can see that that is in fact the case, that these look different. They agree when the real part is positive, but when it's negative, there's a significant difference between those two expressions. And so sort of all these algebraic operations that we learned when we were younger don't necessarily apply. And so now let's look at how to interpret some of these colors. And so let's see. So if we look at sort of increasing values of the argument, so turquoise to purple to red to orange to yellow. I'm going to focus on the red, orange, yellow. So as we go through that, if that is going counterclockwise around a point, then that corresponds to a 0. If it's going counterclockwise and you get multiple times around, then it's a multiple 0. And if you have, say, z to the 3/2, where conceptually it would be like a 0.5 or something. You would see that it would actually go 1.5 times through this cycle, and you'd have sort of a sharp break instead of finishing up the cyclic nature. Poles, on the other hand, you can sort of think of them as reciprocals of zeros, and they go the other way around. So it's red, orange, yellow going clockwise. Multiple poles, the same thing. And then essential singularities, you end up with sort of this infinite cycling through a point. And so we have orange, or red, orange, yellow, red, orange, yellow, red, orange, yellow, and we go through the essential singularity, and then we come back out still going red, orange, yellow, red, orange, yellow, red, orange, yellow. And if you have sort of a higher order essential singularity, then these get sort of really funky looking. But once you start to identify these patterns, then it's very easy to do a complex plot, look at it and go, here are the zeros, here are the poles, etc. So here I'm plotting log of gamma over a particular region. And so red, orange, yellow counterclockwise, that's a 0, that's a 0, that's a 0. I mean, actually, all of these are zeros. There's 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And then some branch cuts where we have sort of sharp transitions from one color to another. And for the curious, here's nsolve telling us what the actual 8 zeros are over the same domain. And so once you sort of get used to what the patterns look like, it's sort of very easy to identify different types of features without necessarily running through a solver that, for a complicated function, might take a while, compared to how long it takes to generate the plot. So the other function that we added was complex plot 3D. This is very similar to complex plot, except we're using height for the magnitude instead of necessarily shading it out to a lighter color. And so this is sort of the recreation of the picture that we had on the very first slide of this talk, which is a recreation of a famous image of gamma by Janka and Imde in 1909, just the publication date for the book this came from. I'm not sure when they actually drew it. And I like to show this just because it's sort of really impressive to me what they were able to do manually by hand in the early 1900s. And I'm just, awed by this, and imagining how much effort this took compared to typing something in and waiting a fraction of a second. And so that finishes up my talk about complex visualization. I'm going to move straight on to geographic visualization, and then following Jason's talk on molecular visualization, we'll start answering all the visualization specific questions. So as I said, in version 12, we are sort of continuing to expand the set of visualization functions for geographic data. And so I'm going to sort of very quickly go through how we might represent geographic data. And so sort of the most common ways are through entities, such as this entity for Chicago. I recall that we have a few, I think it was about 15% people new to the language. And so within the notebook front end, I get this by saying control equal, and I type Chicago, and it helps somewhat if I type it correctly. And let's try that again, because and that's a natural language processing type of thing. There's some flexibility in how I type Chicago. It might do a little bit of spell correction. You know, it's not entirely requiring me to be case sensitive or whatever. And then based on an entity, I can say what's the population. And so for things like countries and cities and common well-known entities or areas, this is frequently a good way to represent or work with geographic data. The other way is through sort of the low-level representation, which is geoposition and that family of objects. And so this corresponds roughly to the city of Champaign, Illinois, where I am right now. So we're roughly at 40 degrees north and 88 degrees west. And so we have geoposition, which is sort of the built-in encoding of that in the language. I can go from an entity to a geoposition in a couple of ways. I can ask for a position property of that entity and get with a little bit more, well, I guess that's Chicago, not Champaign, so the numbers aren't quite the same. Geoposition will also work on entities and extract the same information. And ultimately, under the hood, all the visualization functions are going to be working with geoposition or a variant of that at its lowest level. And when you have a lot of geographic data, it's usually best if you can make use of sort of the multi-form to deal with a lot of the positions at once. So here I'm using a new in12 function to get random geopositions. So 100 points inside the state of Illinois, and so this gives me a geoposition, and this one looks a little bit different from these. And the reason is that this is just a single point, and so it doesn't, I mean, we haven't done anything terribly fancy with it. In this case, there's 100 of them, and so we have a summary box that tells us that there's 100, what the range is, gives us a little plot of what the distribution is. If you squint at this, it sort of looks like the shape of Illinois. And so having that data is sort of a very useful thing. And so in version 12, we introduced 4 new geo-visualization functions. And I'm going to go through them in sort of order of complexity of the data that they take. So the first is Geo Smooth Histogram, which just takes a bunch of geopositions. So here I have about 4,000 locations in the contiguous US, each one representing a brewery. So this was a data set that Michael Trott generated in a blog post a few years ago. And so we'll first just take a glance at a couple of the previous ways that we had of visualizing this. And so we had Geo List Plot, which just draws 1 point for each of those locations. And you can sort of see where they are, but everything sort of, especially in the Northeast here, sort of bunches together, and it's hard to see more detail on what's going on other than there's a lot of breweries here. So then we added Geo Histogram, which is a discrete binning by default using hexagons of the points. And so we can see that there's 133 in Chicago, 73 near Minneapolis, and so on and so forth. And we can sort of see where there's more breweries and where there's less, Denver, etc. And so with version 12, we added Geo Smooth Histogram, which is sort of the analogous to smooth density histogram for non-geo data, which uses kernel density estimation to generate a smooth gradient of values. And so in this case, then we can sort of see the Northeast and Chicago and Detroit, and see sort of where the general trends are. And since it's kernel density estimation, we have a kernel and we have bandwidth, and you have the ability to affect both of those and use them to vary the data a bit. And so if we use a smaller bandwidth, then we get sort of less spread out smoothness and sort of sharper bits of color. This is sort of much closer to our discrete version here. And if we use a larger one, then it spreads out more and you get more diffuse, a more diffuse sense of the distribution. And the other thing that we added for some of the geo functions, and we'll be, I think, flowing this back into more of the core sci-viz functions in the future, is making it easy to say via region function that I want the plot restricted to the US. And so in this case, it's generating the density as before, and then clipping it to the boundary of the US. And so you don't get things that bleed off into the ocean where, say, there obviously aren't any breweries in this data set. And so that's sort of very useful and very efficient way of doing that. So the next function is GeoBubbleChart. So this takes a bunch of locations and some sort of scalar value and plots bubbles on the map for each of those locations, with the bubble size scaled according to the values. And so we see here we have the 25 largest countries in the world by population, and we're representing that by the bubble size. And so we see that China and India are sort of large, and then US, and then things get sort of smaller from there. In the case of something like a country where it's sort of a large region, not just a single point, but we need a single point to place the bubble, then it's put at sort of a center for that location. And so we have a bubble sort of centered in China and centered on India, center of the US, etc. And because this is so obviously this builds on the existing bubble chart of that we've had since version 7, and so it can sort of take use of all of the functionality of the charting functions. So we can add labels, we can do themes to sort of greatly change what the appearance looks like. So using a relief map for the background instead of sort of a more political type map. And so then the last ones that I want to look at is Geo Vector and Geo Vector Plot and Geo Stream Plot. And so this uses a new sort of representation called Geo Vector, which associates a vector with a bunch of geopositions or geolocations. And so in this case, this is a multi-geo position, and then each of them has an associated magnitude and direction. And there's some variant on GeoVector on whether you're using a polar or Cartesian form of the vector. The geo position can be a list of entities, etc. It's very flexible. It can be generated by wind vector data natively. This calculation takes a little bit of time, so I have it pre-evaluated. And so this was the other day, sort of looking at what the wind is over France. So here we have GeoStream Plot first, and it's interpreting all of these as a field and sort of sampling that field and creating sort of streamlines that follow the wind direction. And this is sort of a more continuous type of visualization. Geo Vector Plot is more discrete, where you have just a set of individual vectors showing what the directions are. And similar to bubble charts, these have direct analogs in vector plot and list vector plot and list stream plot. And so we can change the vector marker shape. I believe this option was added in version 11.3 to change what our vectors look like. And just like with Geo Smooth Histogram, we can restrict the stream plot to the outline of, to the borders of France and see what it looks like over just that region. So that finishes what I wanted to say about geographic visualization. I'll leave a little bit of time for Jason to talk about molecular visualization. And thank you very much.
Let's see. Hi. Yeah. Thanks for that talk, Brett. So I'm going to talk today about molecular visualization. The Wolfram language in version 12 introduced a large number of functions for working with molecules. So we're trying to make a more of a jump into the world of computational chemistry, and so this is a step in that direction. Let's see, I'm going to talk, so now I'll go up to 125% here. So what I'm going to talk about mainly first creating molecules, the different ways that you can create a molecule from be it from an entity or a name or a smile string or or a list of atoms and bonds, show you how you can compute properties and descriptor values, and then focus on the main topic, the visualization, how you can make 2D plots with molecule plot and 3D plots. You can annotate those structures, and with molecule plot 3D, it generates coordinates on the fly based only on connectivity, and then using force fields to clean it up. Show how you can do substructure matching to find functional groups inside a molecule, or to take a list of molecules and find a particular substructure in that. And then time permitting, I have a couple of really neat interactive examples showing how you can, given a list of functional groups, you could create an interactive plot showing them, and also symmetry. So that one's really neat. I might fly to the end of it if we're running short on time. So far in the Wolfram language, we've had chemical data starting in version 6. Chemical data features over 40,000 entities, molecules drawn from data sources like NIST and PubChem and Aldrich, IUPAC. And so that all of that stuff, those entities are available in chemical data. If we ask chemical data open close, you get the list of all these entities. Right, and so behind each of these yellow boxes, there are properties, and you can ask for the structure diagram or the melting point. And these are all what we like to call curated properties. These have been brought into the knowledge base from some external source. These are experimentally derived melting points, and so that is in the knowledge base. But so this takes you a certain distance, but then once you get past these 40,000 molecules, you need to move on. And we've got plans to increase the size of this to 1 million, 2 million, but even that is just a drop in the bucket compared to the size of the chemical space. And so, right, so in order to get properties for any molecule you could think of, you would need to be able to create them on the fly and query them for properties. And so that's why we introduced the molecule. Let's see, so this slide just shows the various ways that you can create a molecule. So you can start with defining a list of atoms and bonds. So this has an oxygen, a carbon. It has another oxygen atom with a -1 charge, and then another one. And then it has a bond between the first two atoms, a bond between the second and third, double, and these two are both singles. So we evaluate this and we get back our molecule. It displays in the notebook as a summary box with some information. This is the Inchy key. It's like a molecule hash. So if you take the Inchy key, they're meant to be, you can Google that, and if you find this, there should only be one molecule that generates this Inchy key. And so you could find information about the carbonate if you Google that. Right. And so then once you create it, you can plot it in 2D or 3D. And in both cases, we're generating these coordinates on the fly, not making a knowledge base call. Right. And so then we can use the knowledge base to get the properties. So we have, so here we have propane. This is a yellow box, an entity that represents propane. And if you call entity value on it and ask for all these different properties, you get this amount of information. And that's precisely what molecule does when you give it this propane entity, it converts it into a molecule. And let's see, I should take a time to just point out that molecule plot can work with entities just fine. It will, under the hood, convert it to a molecule, make the plot, and then return it. So if I evaluate this, yeah. So we get this stick figure for propane. You can test equivalence of molecules, so you can create a molecule from the entity or a molecule just from the name propane, and they come back and they say they are the same molecule. Some of our entities represent polymers or non-formulaic chemicals, so those don't translate into molecules, and you get a message. There are a few different shorthands for creating a molecule. So you can use any chemical name. We use the Opsin parser for parsing this, for turning this chemical name directly into a molecule without calling it a lookup table to see what this is. When you evaluate it, it recognizes that you start out with an acetonitrile right here. It's got a phenyl at position 2, and it's got a cyclohexyl also at position 2, and it even tells you about the three-dimensional arrangement of it, right? So, and we display the stereochemistry right in the notebook. And so this happens very quickly. You can evaluate all of these, and I'm continually amazed by how good that this is at parsing chemical names. And I threw this one in just because I'm, like I said, I'm impressed by this stuff. And then so this is 2SN, 1S, 2 carbomoyl, 1. And then I'm going to stop at that point. But in this IUPAC name, it describes the stereochemistry at various points. It describes the substituents, and everything here is everything required to generate this molecule is in that chemical name. And so now we move on to a somewhat less readable but easier for a computer to understand as a SMILE string. And so in a SMILE string, you can represent a molecule. It's like a shorthand. It's so this is an oxygen double bonded to a carbon, single bonded to another carbon, 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 and then there's one last carbon that's off the chain. And hydrogen atoms are omitted if need be, or they can be added. And so this is you can oftentimes find these SMILE strings on the web or in various data sets, and in Wolfram Language version 12, you can easily convert those into molecules. So then when you want to plot the molecule, I've already shown how you can take create a molecule and feed it to molecule plot. There are various plot themes for molecule plot. the number of plot themes is going to increase in future versions, but right now you can use plot themes to control whether hydrogens are shown. By default, some hydrogens are shown, those that are not on a carbon. So here by default, we show these hydrogens attached to the oxygen, but you can say omit all hydrogens, show all hydrogens, show the plotted in black and white. You can add a legend quite easily to show what the different colors represent. Red is for oxygen, blue nitrogen. You can change those color rules easily if you like. You can make all nitrogens in green and all oxygens in this nice little green color as well. And yeah, you can control whether hydrogens are shown. And then we've got molecule plot 3D. Again, we create a sample molecule and we plot it in 3D. And so right then when I clicked enter, it generated 3D coordinates using a distance geometry method and then cleaned them up using the MMFF force field. And so this is a reasonably good structure. Obviously, to get a better geometry, you'd have to feed this to some post-Hartree-Fock method for geometry optimization. We have plot themes for the 3D as well. I'm particularly fond of the tubes where it omits the normal spheres in the ball and stick model. Again, we've got legends and color rules, a lot of the same options as for molecule plot. And then so next we introduce molecule pattern, which is a way to describe substructures within a molecule. So you could, a molecule pattern, you could have just the string O represents an atom, an oxygen atom, or you could have any atom with a formal charge greater than 0 is this pattern, or any atom that is a member of a ring. We can attach those patterns to labels, and so we end up with this association. Now when we feed this to molecule plot, it'll automatically generate the legend and show you that these are the ring atoms, these are the cations, and these are the oxygen atoms in yellow. The same thing works for bonds. You can create a pattern for a nitrogen-nitrogen bond. You can create a pattern for a halide bond for any bond featuring chlorine, fluorine, bromine, or iodine. Or you could create a pattern for a polar bond where the two atoms in the bond have opposite partial charges. So in this, one atom has a partial charge greater than 0.2, one atom has a partial charge less than minus 0.2. And when we feed this to molecule plot, we can see that it highlights the nitrogen-nitrogen bonds, the polar bond, and the halogen bonds. Finally, then you can create a bigger pattern than just two atoms in one bond. You use molecule pattern for that. And it's got the same argument structure as molecule: list of atoms, list of bonds, and then it works in the same way. So this shows where the carbonic ester functional group is located in this particular molecule. You can do substructure filtering. This is fairly neat. So here I've got an iconized list of 3,000 smile strings. We create the molecule by entering that, and notice it was rather quick. And then we create a pattern for ether, for a diaryl ether. This is an aromatic carbon atom bonded to an oxygen, bonded to another aromatic carbon atom. So we've got moles, you'll see, is a list of 3,000 molecules. Let's see, so this is what the ether pattern represents. And now you take that list of molecules, put it into select, and say molecule contains Q ether pattern. And right away it comes back and says that there were 40 molecules in that with the ether. And so then you can highlight all of those in a grid of plots. And I'm really running out of time here. Yeah, So that took a second to produce. But here it shows all the different cases where you have the diaryl ether. And yeah, so then I will flip and just show these fairly briefly. This is an iconized list of functional groups taken from this web source on the web. You can create an interactive plot here where you can say highlight charged, highlight aromatic atoms, highlight nitro, dialkyl ethers. All right, and then finally, here we go. You can create, let me just show what the code looks like behind this. So this is relatively simple code here. And so you evaluate this and it'll automatically create this molecule, create the 3D coordinates, and then figure out the point group was tetrahedral, and then show you, and then you can show all of the like the C3 axes. You'll see there's one C3 axis along each carbon nitrogen bond, and you've got all the, you can show all the different planes of symmetry. Yep. And I am definitely out of time, so
Okay, so I'm going to try to tackle a couple of the questions that have come up. Starting with sort of the complex visualization. And so one of the questions, or actually a few of the questions that come up are with regard to the use of color in the complex visualizations. And sort of we've chosen defaults for the complex viz, and AbsArgplot and complex plot 3D are all using the same sequence of colors that goes from turquoise to turquoise, sort of in a cycle. But this is configurable, and so I mean, first I'll just comment because is that this color sequence isn't quite just hue. It's been adjusted a little bit so that we don't have quite so much variation in brightness. Otherwise, sort of the turquoise would be cyan and be super bright, and same with yellow. And so we've sort of balanced it out so that things are sort of evenly weighted a bit in this color system, in this color scheme. That said, as with pretty much all visualization functions, you can change what scheme you want to use. So if you want a non-cyclic color function, then by all means set it to something that isn't cyclic, such as rainbow, or I think if I did, is it grayscale? Gray tones. Then you get sort of non-cyclic, and that shows off some of the branch cuts a little bit better, where it jumps from pi to minus pi. In particular, gray tones might be better for purposes where you're doing black and white reproduction, or you want to be especially have people with not full color discernment. And so that's a possibility. The other thing that I didn't really cover in my talk for time considerations is that there's a lot of variations on our lightness scheme. And so here I'm going to set it to a cyclic log abs. And so then in this case, in addition to the color changing with the argument, we're actually also varying the lightness and darkness on a sort of powers of 2 basis according to the absolute value or the magnitude. and these are reasonably well documented on in the documentation for complex plot. But there's a lot of flexibility in complex plot, in complex plot 3D for changing what the coloring is used. It supports plot theme, which bank switches lots of things. And basically all of these functions support all the normal options for label style and legends and whatnot. And so I think that covers most of what the people were asking about for the complex viz. For the geographic viz, then we're aware that sometimes the default maps are a little bit blurry, and that is high on our list to improve. And so and if you play with geo background, you can there's some vector forms there in terms of like country borders and whatnot, and then also if you want, you can point to your own to a different geo server, a different source of background maps using the geo server option. And then the other questions for the geo stuff, I think, was mostly little things, but I want to hit them as quickly as I can. So the breweries data, this is a data set that I processed elsewhere and copied into this notebook to save time and space. When I get a chance, I'll try to put a link to Michael's blog post where he derived this. For geoposition, so these are latitude and longitude. It is possible for these to contain altitude as well. For the most part, we don't include it in a lot of things by default, but it is possible to represent it there. And I'm thinking about actually making use of that for some future GeoViz functions. I mean, and actually this can even be time-stamped, although I'm not going to try to input that by hand at the moment. Although it does arise occasionally, especially if you get like position information for satellites. Then you get sort of geopositions with high elevation and very specific timestamp on where the space station was at a particular instant. And so the region function specification that we used, I'm not going to try it right now. It should work with arbitrary polygons. It might be a little bit slower, but it really shouldn't be. It may be though that it's a little bit of work to get it in just the right form. I mean, because you need to make sure that you have a polygon of a geo position and that the coordinates are specified on the Earth for it to sort of clip out the correct region. And so I think that covers most of the immediate questions that I saw. And so now I'll turn it over to Jason if he has any questions that he would like to answer. So thank you.
So there was a question about ignition points and whatnot. And so we do have some data. We won't have that data for everything, but the way I got here was I just typed in control equals butane ignition point. And so it comes back as showing me that we have a property called a chemical property called auto ignition point. And for butane, it is populated. Probably for maybe for other molecules, it might not be populated. So that depends on access to curated data. Someone asked about trimethyl sterile ammonium, and so we're able to parse that chemical name directly to a structure, and we can generate a 3D plot from it So this guy is going to be a big floppy molecule. So the percentage of the time that it spends in this particular configuration, I don't have enough information to say, but it's a reasonable structure. Someone asked about reactions. We're definitely interested in adding chemical reactions in a future version. For now, we have a molecule modify, which can change a molecule. So in this case, I create N-hexane, which is a straight chain of 6 carbon atoms with hydrogens, and I add a bond between the first and the 6th carbon, and it will create cyclohexane. You can then take that cyclohexane and add a bond from any of them to an oxygen, an external oxygen, and so you can create a cyclohexanone. You could also set a formal charge. A lot of these are spelled out more in depth in the new Inversion 12 marketing page for all of this stuff. Someone asked about movies, so it would be great to be able to make connection to MD simulations, either running them directly in the Wolfram language or just connecting to a program that's made to do that. The PDB database. So right now, importing a PDB into a molecule is not hooked up. I was able, before version 12 came out, I got mol files, XYZ, SDF files, mol2, but PDB is at the top of the list for the new formats. And we're also definitely interested in crystalline, non-molecular chemicals. So solid state. It would need some new head. They wouldn't just be molecules. I think some hunk of germanium or something. So it's going to have a lot of different things inside it: the lattice, the coordinates, the different properties or whatnot. And so that's something we're interested in doing, but we don't have a proper design for that. What I'd like to say is if there's any stuff that you want for chemistry, send us feedback in some way or another, and that can help to guide where we go in the future.